So if it's going, I would like to greet everybody and welcome in this session. This is the next part of our seminar for mathematical physics. Today with a hybrid form, which is going due to our speaker today, Eyal Subag from the Bar-Ilan University in Israel. And Eyal is going to talk about the very interesting topic, families of symmetries in the hydrogen atom. So thank you very much for accepting the invitation, and we look forward to what you're talking about.
Thank you very much. And thank you for the opportunity to speak about my research. I hope that there will be no technical issues. I don't see the people that are in class. So if you have any questions at any time, let me know, and I'll do my best to answer. Okay, so I'll talk about the hydrogen atom, one of the basic quantum mechanical systems. And I'll try to show you how algebraic families are hiding within this system. So this is based on a joint work with Nigel Hickson. And in fact, it goes back to, I mean, the algebraic families subject. This is joined together with Nigel and Joseph Bernstein, but the part on the hydrogen atom that I represent is due to my work with Nigel. In any case, let's start with motivation. If you take hydrogen gas, and if you give it energy, if you hit the gas, at some point it will emit light. If you let the light go through a prism, you'll see such a pattern of emission spectrum, some distinct wavelength within the visible range, the visible light. And a basic question is why? Why do we get something like this, something which is discretized or quantized? What is the reason? If you're the first person that can answer such a question, then if you're lucky, you can win a Nobel Prize. And this is what Niels Bohr did. And let me remind you, I'm sure that most of you are familiar with this. Let me remind you the Bohr model for the atom, so for which explain quite well this discrete pattern that we see. So a hydrogen atom consists of one proton, and it is circled by one electron. That one is charged positively, the other negatively. There is an attractive force between them. So Bohr's model, or Bohr's idea, was that there are only certain allowed radii, and not only that there are only certain allowed discretely many, countably many radii, there is a minimal one, there is the smallest one. And the smallest the radii, the smaller the energy. It's a more stable state. So the electron or the system would prefer to lie on the closest orbit or the smallest radii. And if you give, so this is the typical state that you will find hydrogen atom. And if you give it energy, then the electron can go to one of the other layers, other orbits. And after some time, it would like to get back to the more stable state. So the electron will bounce back to the lower radii. And by doing so, to preserve energy, it will emit a photon. And the energy that the photon can have is exactly the difference in energies between those two levels or layers or orbits. And they come only in those prescribed discrete values. So this is the basic mechanism that explain why we see such a quantized phenomena. And in a more precise manner, if you want to get some actual quantities or things that you can calculate to describe the system, you can use the Schrodinger equation. So the Schrodinger equation, or the time-independent Schrodinger equation for the hydrogen atom system, it's an eigenfunction, eigenvalue equation. You solve this equation. H is a differential operator. The differential operator is the negative of the Laplacian minus 1 over the Euclidean radius, the Euclidean distance. And you solve for all functions. You look for all complex numbers, eigenvalues or energies for which there is a non-zero solution. A solution is a function on space. And in physics, you typically demand some boundary conditions. You look for functions that are good at zero, good at infinity, and you also, a typical thing to look, and this is what we'll do, you look for functions that are, for example, you can say it like this, you look for separable solutions in polar coordinates, for example, or functions that are well behaved under the action of the rotation group, SO3. So the collection of all such energies, all such complex numbers, this is the spectrum, and the solution spaces, namely the kernel of this operator, H minus the scalar E, these are the solutions. These are the interesting solution space, and you need to specify which kind of solutions to get the right space of solutions. But in any case, this is the problem. Once you know the spectrum, once you know all the energies, and once you know all solutions, then if someone is giving you the state of the system, some arbitrary state of the system, you know how it evolves in time. The Schrodinger equation tells you how the system will, what is the dynamics of the system, and in that sense, if someone is giving you an initial state, you'll know the state in any time. The solution, namely the spectrum and all solutions, is well known. Physicists know it for many years. It goes back to work of Pauli, Fock, and Bergman. And in all, or in most cases, it involves symmetry. There is some obvious symmetry that all of you can see, which is this operator as this rotational symmetry, SO3 symmetry. You can use the orthogonal group SO3 as a symmetry group, but in fact there is a larger symmetry, a hidden symmetry, which is some other Lie group containing SO3. And in fact, there is more than just one hidden symmetry. There are three hidden symmetries, and the type of group or the correct group depends on the spectrum, on the sign of the energy. So first, let me tell you what is the answer for the spectrum. So first of all, the spectrum consists of real numbers, consists of all positive numbers, including zero, and a sequence of negative numbers proportional to 1 over n squared, converging to zero. So depending on the energy that will take in the spectrum, the hidden symmetry can be seen in the following way. The solution space, take an energy in the spectrum. The corresponding solution space will give rise to a unitary irreducible representation of a hidden symmetry Lie group. If the energy is negative, it will be a finite dimensional unitary irreducible representation of SO4. If the energy is positive, we'll get an infinite dimensional unitary irreducible representation of the connected component of this Lorentz group. And if the energy is zero, we get a representation, unitary irreducible, of the semi-direct product, this Euclidean group, or also called Cartan motion group. So this is one way to see the hidden symmetry, or the hidden symmetries. There are also other ways, more algebraic. Some involve some more sophisticated things in analysis. But in any case, you can express it in terms of representation theory. What type of representation is the corresponding solution space? If you look on those solutions, those psi, the absolute value square, if they are a solution, the absolute value square give us a probability density for what are the odds for a particle to lie at a certain region in space. If you project this on a plane, you get those nicely looking diagrams that you see in front of your eyes, those patterns. And as you can see, there are many different options. I should mention, it was not clear on the previous slide, that besides the energy, which is a parameter which lives there are other parameters that at this point you can think of as separation constants, which give us the different possibilities. So one thing is the energy, another thing are some separation constants, or if you're familiar with the language, some other good quantum numbers. What is the plan for the rest of this talk? So I will first explain a little bit about algebraic families. What are algebraic families of groups, Lie algebras, families of representations. I will then relate those hidden symmetries that I mentioned. I will show how you can describe them using this language of algebraic families. Mainly, I will talk about, at this point, families of groups and Lie algebras, families of Lie algebras. And later on, I will talk about solutions of the Schrödinger equation, different type of solutions initially than the ones the physicists are using. And I will explain how those solutions form algebraic families. There will be algebraic families on which those families of symmetries act, families of groups. And at the very end, I will relate those abstractly, algebraically defined families of solutions. I will relate them to the physical solutions that you can find in, let's say, textbooks in quantum mechanics that take the hydrogen atom as an example. So let's start with algebraic families, with families of Lie algebras. So let's describe what is an algebraic family of complex Lie algebras over a complex algebraic variety X. So such a family is, this is a locally free sheaf of OX modules such that carries this sheaf of section. It carries a Lie bracket map. Lie bracket, something that satisfies the usual condition for Lie brackets, Q-symmetric, Jacobi identity, but it will be linear over O of X, not over the complex numbers. And for this talk, I will only care about a very simple case. The variety, the base variety, or the complex algebraic variety will be just the complex affine line, just complex numbers. And in such case, an algebraic family of complex Lie algebras is simply a free Lie algebra, not over a field, but over this ring of polynomial functions in one complex variables. So it's just a Lie algebra over this ring, which is also free as a module. So it's quite simple. Let me show you some examples. So the basic example, the most simple example is, in some sense, constant families. For example, you can consider 4x4 matrices with entries being taken from this polynomial ring. This is, of course, a Lie algebra. You can use the usual commutator of matrices, and it will be a Lie algebra over C of Z. But a more interesting example is this family, which you can see in front of your eyes. So all entries are polynomial functions in one variable, and there are those relations that there is this upper left 3x3 block, which is skew symmetric, and there is this blue part where whatever you see on this column, you have here it's transposed, but there's this, it is multiplied by this by the variable, namely these are polynomials that vanishes at 0. So this is an example for such a family. Why I'm calling it a family? Because if you have such a module, such a Lie algebra of a C of Z, you can take fibers. You can choose a complex number T. This complex number T gives you an ideal in this polynomial ring. It gives you a submodule for G, and you look on the quotient, and the quotient is a complex Lie algebra. And in this specific case, it comes in two flavors. If the parameter, if the complex number is non-zero, this is the generic case, you get a copy of the complex 4x4 orthogonal, this SO4C, skew symmetric 4x4 complex matrices. If T is 0, if the parameter is 0, you get this complex semi-direct product, SO3C semi-direct product with a three-dimensional complex vector space. Another thing, so this is a good thing to keep in mind. If you have a Lie algebra of a C of Z, out of it you get a collection of complex Lie algebras. This is why this is, we treat it, this is why this is a family. And as for complex Lie algebras, for which you have the notion of an anti-holomorphic involution or something like complex conjugation in a corresponding real form, there is a good notion for families of complex Lie algebras. There is a good notion of what is an anti-holomorphic involution. And in our case, in this example, always for families, there are two involutions. There is an involution downstairs on the base variety, which in our case is just complex numbers. And the involution is just complex conjugation. Alpha goes to alpha bar. And there is an involution upstairs, which in our case will be just entry-wise complex conjugation. Such a pair of involutions defines an involution for the family. And if you have such an involution for the family, from a family of complex Lie algebras parameterized by complex numbers, you get a family of real Lie algebras parameterized by the real numbers. What you do is you take a T, which is real, T in the fixed points of the involution of the base variety. Above it, you have a complex Lie algebra, along with an anti-holomorphic involution. You look on its fixed points. In our case, it simply boils down to look on all real matrices in the fiber, in the complex fiber here. And the result in this example is that you see three different real Lie algebras depending on the sign of T. If T is negative, you get the real Lie algebra SO4. If T is positive, you get SO31. If it's 0, you get this semi-direct product, which are the Lie algebras of the group I've mentioned before as hidden symmetries. What about groups? What about families of complex algebraic groups? So formally, a family of complex algebraic groups is over complex algebraic X. It is just a smooth group scheme over X. And in our case, we'll use just a couple of examples throughout this talk. A basic example for such a group scheme is a constant group scheme. Namely, you take a complex algebraic group like SL4C, 4x4 determinant 1 complex matrices, and you take its product with the complex affine line, and this form a constant family of complex algebraic groups. And inside of it, let us look now on an interesting subfamily which is not constant. Let's define a family G such that its fiber over Z is a point in the base, its fiber over Z will be the group of special automorphisms of the quadratic form, which is this linear combination of squares, x1 square plus x2 square plus x3 square minus the parameter Z times x4 square. Was there a question? No. Okay. So if Z is non-zero, then you get a copy of SO4C, the complex group SO4C. But if Z is zero, you get something different. You get the semi-direct product. You get this group. This is a matrix in block form. A is orthogonal 3x3 matrix. V is a vector. This group is isomorphic to the semi-direct product, O3 semi-direct product with this vector space. And again, in this, for groups, for families of groups, there is also a notion of anti-holomorphic involution and the corresponding real forms. And the anti-holomorphic involution here is again given by entry-wise complex conjugation. If you look on the fibers and if you look on if you look at base point which is real, and if you look on those real matrices in the fiber, you will get the real Lie groups that you would expect from the previous example that I showed you at the Lie algebra level. You will get SO4 for negative T, you will get SO31 for positive T, and for the zero case, for T equals 0, you get this Euclidean. There is also a natural algebraic involution here. Using this matrix form, you can fiber-wise conjugate by the diagonal matrix 1, 1, 1, minus 1, and it's an algebraic involution in the sense that it's a morphism of group schemes, and its square is the identity, and the fixed points give us a constant family. It's a constant family with fiber being O3C. Then it will play a role later on in the rest of this talk. Any questions before I leave these examples? Very well. So let me just say that the game that we just played for SO4 and SO31 can be played for SO, let's say n plus 1, SO n comma 1. And if you consider the case of SO3 and SO21, then I can give meaning. We can give meaning to this deformation parameter, to the base parameter, its real version. So we have in this real case, we have a family of groups interpolating between SO3 and SO21, and they all contain the subgroup SO2. They all contain SO2 as a subgroup. So if you mode out by SO2, you get a family of homogeneous spaces. And if you're in the case where the parameter is positive, the homogeneous space is a two-sheeted hyperboloid. If the parameter is 0, you get those two parallel planes. And if the parameter is negative, you get those ellipsoids. They all share the north and south pole, but it tells us that this parameter, this deformation parameter, is related to curvature of these homogeneous spaces. So mathematically, we can relate it to curvature. In a minute, I will try to convince you that we can think of it for the hydrogen atom system as some sort of the energy, some generalized energy. Before moving forward, I will need some language from algebraic representation theory of reductive groups. Let me say a few words about what are Harish-Chandra modules and Harish-Chandra pairs, and then I'll talk a little bit about families of such things. So suppose that G is a reductive Lie group. If you don't know what it is, think about SL2R. And such a group contains essentially unique maximal compact subgroup K. In this example of SL2R, you can take K to be SO2. Then out of this object, this thing which is in the world of analysis, a Lie group, a group which is also a smooth manifold such that all the structure is compatible, you can get something in the world of algebra. This thing in the world of algebra, one thing is that you can get in the world of algebra is a Harry-Chandra pair. What is a Harry-Chandra pair? It's a pair consisting of a complex Lie algebra and a complex algebraic group. In our case, it would be a complex reductive algebraic group. What do we do in this case when we start with this reductive Lie group? We take the Lie algebra of our real group, which is SL2R, we complexify it, and we get SL2C, traced to 2 by 2 complex matrices. We take our maximal compact subgroup, and this can also be complexified, and its complexification is complex reductive algebraic group. In this case, it will be SO2C. And out of this, let's say, smooth object, G and K, you end up with something in the world of algebra, this fractal G and this complex algebraic group K. And why is it important? It is important because you can use it to study representations of G and in fact classify a good chunk of these representations. So first of all, before explaining more on Harry-Chandra module, so let's just summarize. A Harry-Chandra pair is a pair consisting of a complex Lie algebra and a complex algebraic group K, or K of C. And I already explained what is a family of complex Lie algebras and what is a family of complex algebraic groups. So an algebraic family of Harry-Chandra pairs over a variety, complex algebraic variety X, will consist of two such families of Lie algebras and complex algebraic groups that satisfy some natural compatibility conditions. For example, in the classical case, to get a sense of what type of compatibility conditions, the Lie algebra of this complex group is embedded into this Lie algebra G, and this complex group acts on this G, and the embedding that I mentioned is equivariant under the natural action of K on its Lie algebra and on G. Let's move to representations, and let's see how we can take a representation, which is some continuous thing, and get out of it a module for this algebraic thing. So suppose we start with a representation of our reductive group G and some topological vector space V. Then it's a simple thing to get an algebraic module, a GK module, a module for this Harry-Chandra pair GK. And what do? You simply take K finite vectors. What are K finite vectors? These are all vectors in V that under the action of this maximal compact subgroup K, they generate a finite dimensional complex vector space. All vectors that generate a finite dimensional space under the action of K. For example, in this example that I've mentioned before, SL2R, you can realize many representations, all principal series representations of SL2R on square integrable functions on the circle. And you can realize this representation in such a way that the maximal compact subgroup, SO2, which is the group of these rotations, will act on a function on the circle by just translating the argument, by left translation. And to be a K-finite vector in this L2 space, which is L2 space is something in analysis, it's not something in algebra. So to be a K-finite vector, it just means that you can be expressed as finite linear combination of the usual Fourier basis, some trigonometric polynomial. It's a very simple thing. It's linear algebra and not analysis. So to move from L2 space to some finite dimensional thing, it's a big simplification. And it's a fact that this K finite subspace carries an action of G and an action of K, these complex algebraic things, and these two actions are compatible in some natural sense. And this thing, a complex vector space carrying two compatible actions, this is what we call a GK module. Now let me explain what is a family of such. So suppose we have an algebraic family of Harry-Chandra pair over some variety X. What is such a GK module, or what is an algebraic family of Harry-Chandra module over this X, this complex algebraic variety? So we replace the complex vector space by a sheaf of OX module. It should be a nice sheaf. The correct technical term is it should be a flat sheaf of OX modules, and it should carry an action of this sheaf G or this family G, and an action of this family K, and the actions should be compatible. Once we understand the classical notion, which I haven't spelled out explicitly, it's a simple thing to understand the definition for the family. The family presents no further complications. Good, so this is what I need from representation theory. Now I can get back to the hydrogen atom. And the next goal in the next few minutes would be to build an algebraic family of Harry-Chandra pairs out of the hydrogen atom, out of the, if you want, the Schrödinger equation of the hydrogen atom. This is what we are going to do. The starting point, so recall our Schrödinger operator is the negative of the Laplacian minus 1 over R. So this differential operator, it acts on smooth functions on the complement of the origin in R3. So let's consider the algebra of all differential operators on smooth functions on the complement of the origin in R3, complex valued functions. This is an algebra. It is filtered by the degree of a differential operator. And in quantum mechanics and physics, once you start with a Schrödinger operator or a Hamiltonian, one of the first things that you do, you look for symmetries. You look for things that commute with the Schrödinger operator. So let's do what the physicists are doing. Let's consider the centralizer of our Schrödinger operator in this algebra. So we look on this centralizer. The centralizer is a subalgebra, namely a complex algebra, but it is more than that. It is also an algebra over polynomial functions in H, polynomial expressions in H. H is the Schrödinger operator, because H commute with everything in the centralizer, and all expressions in H commute with the centralizer, or commute with anything in the centralizer. So recall my remark when we talked about families of Lie algebras, which are the same as a Lie algebra over a sea of polynomial functions in one variable. So the same goes in this associative algebra case. What we got here, we obtain the centralizer. We notice that the centralizer is an algebraic family of complex associative algebras over complex numbers. You can think of complex numbers in more algebraic language as the maximal spectrum of this ring, but just over the complex affine line, just complex numbers. So we have a family of complex associative algebras. I would like to get out of them a family of complex Lie algebras. We'll do it slowly. First, let me show how we can get the family of groups. So know that O3, as I mentioned before, it acts on the Schrödinger operator. It acts on the algebra of differential operators on the complement of the origin. It acts on the centralizer. And this action gives rise to an action of the constant family K, with fiber being the complex orthogonal group O3C. So we get an action of this constant family of groups on the centralizer. And I'm going to look now on a small piece inside this centralizer. I'm going to look inside this centralizer. I'm going to look on all differential operators that are of degree bounded by 2. Differential operators of degree bounded by 2. And this subscript adjoint edge stands for, I'm going to look on the action of SO3 on this piece. It is stable, or it carries an action of SO3. You can restrict the action that I mentioned a minute ago. And you can decompose this space into irreducible representations of SO3. I'm going to look on those pieces that isomorphic to the adjoint representation of SO3 on its Lie algebra, if you want, the standard representation of SO3 on a complex three-dimensional vector space, the standard, the usual representation that you are all familiar with. So look on this piece, something with respect to the action of SO3 and something that takes into account the degree of a differential operator. And I want to define G, bold G, as the C of H module generated by this piece, this chunk that I chose. This all lives inside the centralizer of H, which is a module for C of H. So it does make sense to define G in such a way. And the claim is that this G that we just defined, together with this K, this constant family that we just defined, it forms an algebraic family of Harishchandra pairs over X. So in this way, using the concrete realization, the physical realization in which we typically encounter the Schrödinger equation for the hydrogen atom, you can get this family of Harishchandra pairs that I mentioned earlier today. Let me show you some part of the proof of this theorem, not all of it. So first, I can tell you that you can do a calculation. You can just calculate, it's a finite dimensional complex vector space. You can calculate all differential operators of degree less or equal to 2 that transform under the action of SO3 in the way that I specified before. And you can see that this is a 6-dimensional vector space spanned by those Li's and Ri's. The Li's are the usual generators for rotations, the differential operators that generate rotations. The Ri's, if you're familiar with the Kepler problem, then the hydrogen atom system is a quantization of the Kepler problem. And in the Kepler problem, there is a constant of motion which is known as the Runge-Lenz vector or Laplace Runge-Lenz vector. And its quantization give rise to those Ri's. Explicitly, they are given in the following form. Don't get intimidated by all those symbols. The important thing is that they are second-order differential operators. This partial 2 is just derivative with respect to the second coordinate. This is a first-order differential operator, but this L3, it's also a first-order differential operator. Altogether, this term is a second-order differential operator, and this is indeed the second-order differential operator. As you can guess, by the way, this span of the Li's generate a copy of the three-dimensional irreducible representation of SO3, and the same goes for the Ri's. They generate an isomorphic representations of SO3. So as a set that we use to generate G under the action of C of H, this is the set, the collection of the Li's and Ri's. Next step, you look on, all of these are concrete differential operators. You can look on their commutators. Those epsilon ijk's, if you're not familiar with them, these are just numbers. These are 0, plus, or minus 1, but just complex numbers. In fact, just 0, plus, or minus 1. The commutator of two rotations is a rotation. The commutator of a rotation and a Runge length component is again a Runge length component. But if you take a commutator of two Runge length components, then if it's not zero, you will get a rotation times this Schrödinger operator times h. Namely, the span over C, this space, it's not closed under brackets. It's not a Lie algebra over C. But if you look on what it generates under the action of H, then it is a Lie algebra over C of H. And this is hiding in here. Usually in physics, in textbooks, what they do is they restrict their attention to eigenspace, and then H becomes a number, and then they normalize the generators separately for positive, let's say for the positive sector and separately for the negative sector, and they are just left with SO4, and they just ignore it. So this is a part of the story why this is an algebraic family of Lie algebras. What is left, and I will not show right now, is that this module over C of H is indeed free. There are some involutions, some natural involutions in this realization. This realization, I remind you, this G was generated by those Li's and Ri's, which are concrete differential operators on functions on R3, take away the origin. I can think of each of those differential operators as an operator on smooth compactly supported functions on R3, or R3 take away the origin. And I can use the adjoint or the negative of the adjoint, the family that we just defined a minute ago is stable under this map. And in fact, it defines an anti-holomorphic involution of G, something like a complex conjugation. There is another anti-holomorphic involution for the group. I can think of each element of K, O3, also as an automorphism of smooth compactly supported functions. And I can again use the adjoint and the inverse of the group, and I get an anti-holomorphic involution on the compact, excuse me, not compact, but on the family of complex algebraic groups. These two involutions together, they give us an anti-holomorphic involution for the family of Harish-Chandra pairs. And in fact, there is another involution that I'm going to describe right now, another involution for the family of Lie algebras, which does not involve the formal adjoint, but you can also define an involution in the following way. Each differential operator on R3 take away the origin can be written as just powers of the standard partial derivatives or standard vector fields times smooth functions on R3 take away the origin, complex valued function. If you just take complex conjugation of these coefficient functions, this is also an anti-holomorphic involution of this family. Out of these two anti-holomorphic involutions for G, since you can do a small calculation and see that they commute, you can compose them. It doesn't matter in which order, of course. You can compose them and you get an algebraic involution theta of this family of complex Lie algebras. And the statement of the next slide is that all this structure, we have a family of Harish-Chandra pairs together with certain involutions that arises from the Schrödinger equation of the hydrogen atom. All of this can be lifted to the group level. And in fact, what I'm going to describe in this theorem, it's just the second example I showed you for a family of complex algebraic groups. And the statement is that there is an algebraic family of complex algebraic groups, G, over the complex affine space, equipped with an anti-holomorphic involution sigma and an algebraic involution theta, such that out of these involutions we'll get the family of Harish-Chandra pairs. The fixed points of the algebraic involution is the family of groups that we saw before. And for families of groups, the ones that we are working with, there is a good notion of a Lie algebra. The Lie algebra of this family of groups in the theorem is exactly the family of Lie algebras that we encountered a few minutes ago. Moreover, because we have an anti-holomorphic involution for the family of groups, we get a family of real groups parameterized by real numbers. The real groups that we see are exactly those that appear before, depending on the sign of T, either the compact SO4, the Lorentz group SO31, or this semi-direct product. And as a result, I can suggest the following thing for physicists or for everybody who is interested. I suggest that the hidden symmetries of the system in the level of groups and Lie algebras would be described in the following way. The basic object would be a family of complex algebraic groups G and two commuting involutions. One is algebraic, the other is anti-holomorphic, the other is like complex conjugation. And once you are given such a data, you can easily recover the hidden symmetry and the visible symmetries. The hidden symmetries, you'll just take the family of complex algebraic groups and look on the corresponding family of real groups, the fixed points of the anti-holomorphic involution. If you want to get the visible symmetries, in our case these are O3, you just iterate fixed points for theta and sigma. And this will give you the hidden symmetries and the visible symmetries. So you can replace the setup to work with those family of groups together with the involutions. So I see that I have 12 minutes and approximately 8 slides, which means that I'm going to condense some of the slides, but not the next couple of ones. Let's start and see where I need to move faster. So I explained to you how to think about hidden symmetries at the level of groups and Lie algebras in the sense of algebraic family of Harish-Chandra pairs and algebraic family of groups. And now I would like to treat solutions. I would like to look on solutions for the Schrödinger equation and to build out of them algebraic families of Harish-Chandra modules for this family of Harish-Chandra pairs that I introduced. So first step is consider this solution space. E is an arbitrary complex number. Look on all smooth functions on the complement of the origin that are K-finite, that behave well under the action of SO3, that solve the Schrödinger equation with this specific energy, with this specific complex number. And consider separation of variables. Look on separable solutions with respect to polar coordinates. So you get two things. You can write each solution as a linear combination of functions of the radius times function of the angles. And more than that, you can decompose your solution space according to the separation constant, or equivalently, according to irreducible representation of SO3. You have this L, this separation constant, which is a non-negative integer. The spherical part, it's essentially a spherical harmonic. It's a linear combination of spherical harmonics, which are familiar special functions that appear also as representations of SO3. The radial part is a solution of a second-order linear differential equation. A general theory of such equations guarantee that we'll have solutions with good behavior near zero. I'm going to define for a fixed E, fixed complex number, and a fixed L, a fixed separation constant. I'll define what is this regular solution, reg sol EL. I'm going to look on all solutions in this space, in sol E, and you see there is this subscript L, namely that they satisfy this equation. In this equation, L appeared. And I also demand that they are bounded near zero. My solutions are not defined at zero. These are smooth functions on the complement of zero. And from this general theory, we also know that the solution, there is a solution starting, if you can write it as you can expand it in powers of R, where the leading term near 0 would be R to the L. L is the separation constant. I'm going to use this information to define an algebraic family of Harishchandra modules. So for every such separation constant, such L, let's consider some space of sections, space of functions. What are those functions? These are functions for the complex field. For any E, you'll get the function on the plane, a function not on the plane, on space, on the complement of the origin. They will be a product of a radial function times the spherical harmonics with the correct L. And you want to be in this reg sol along with another demand, which is regular leading coefficient, which I'll explain right now. You can expand the radial function into power series, into powers of R, but we'll demand that the coefficient, which is now a function of the energy of this pseudo energy, this complex energy, will demand it to be a polynomial function of the energy, a regular function of the energy. Now, if you look, so on such a thing, of course, the Schrödinger operator acts. It can act trivially by just multiplication of this function by E, because these things are eigenfunctions for the Schrödinger equation of this specific E. So on this type of expression, H acts, so C of H acts, and also on this part, the orthogonal group SO3 acts. So let's define regsol with no parameters as the C of H module that is generated by consider all such things as L varies on non-negative integers, and let H act on everything, C of H act on everything. It's not complicated to see that this thing that we just defined, it's a nice it's a nice C of H module, and it's also not complicated to see that it has a good action of K, the constant family of groups with fiber SO3. But it is much more difficult to see that this type of functions are stable under the action of this family of Lie algebras that I concretely defined for you using those differential operators, L1, L2, L3, and R1, R2, R3. So the statement is that they form a module, an algebraic family of Harishchandra module for this family of pairs that we considered before, and more than that, it is generically reducible in some sense that you can easily guess. I'm assuming I have 5 minutes. Am I correct?
Yeah, more or less 5 minutes, or if you need a bit more, it's no problem.
Okay. So I'll try to shorten what I can. We'll see how I can do that. So let me go over this slide relatively fast. Consider the more general case that you have an algebraic family of Harishchandra pairs. You have a family of modules for this pair. This F is a family of modules. If you take a base point, then the fiber of this sheaf, this family of modules, give you a Harishchandra module for the classical Harishchandra pair you get by taking fibers. If your family of groups is constant and the fiber is complex reductive algebraic, you get a decomposition according to irreducible representation of this constant group K. So you have a decomposition of a family of some sheaf into subsheaves, and if all of these are coherent, then you call it quasi-admissible. If they are all finitely generated, finite dimensional in some good sense, then you call it this sheaf quasi-admissible. If a sheaf is quasi-admissible, then there is a good action, a nice action of the center of the enveloping algebra of G. We have G, the family of Lie algebras. It has a universal enveloping algebra, and it has a center, Z of G. In classical case, you are all familiar with Schur's lemma that tells you that on irreducible things, the center acts via multiplication by scalars. In this setup of families, if you have something like Schur's lemma, you'll demand that the center will act by not scalars, but scalars are now regular functions. And they come from some map that is a homomorphism of algebras over X. Okay. So let's get back to the family we had before, family of Harishchandra pairs that I gave you in the second or first theorem, the one coming from physics, from the Schrödinger operator. Let me remind you that irreducible representation of SO3 are parameterized by non-negative integers. For each such L, WL is a representation of dimension 2L plus 1 that you can think of if you are familiar with spherical harmonics. You can realize them as spherical harmonics that appeared before. Let's define a certain class of families of Harishchandra modules. These are called standard and spherical. What are those? These are families that that the isotypic decomposition is as follows. Each piece that corresponds to an irreducible representation of SO3 is obtained in this very simple way. You take a representation of SO3 and you do scalar extension, you extend it to be a sheaf of OX module by just tensoring it over C with O of X. And you have one more condition. You want the piece that corresponds to the trivial one-dimensional representation of SO3. You want it to generate your family, your sheaf, under the action of the enveloping algebra. You can do, so you can classify such, I'm going to explain that you can classify such standard and spherical families. And ingredients for classifying such are the center of the enveloping algebra. You can do a calculation. This is a technical thing. You can calculate that the center of the enveloping algebra of this family of Lie algebras is generated by three terms. R dot L is R1 times L1 plus R2 times L2 plus R3 times L3, and so on. And you can show that a standard and spherical family or module for this family of Harishchandra pair GK is quasi-simple, namely the center acts on it nicely. And more than that, its isomorphism class is completely determined by the way in which this element acts, this specific central element. Since I don't have a lot of time, I'm going to skip the next few slides. I'm just going to briefly explain. I've mentioned what are standard and spherical, the fact that you can classify them. Similar to the regular solution case that I described, there is an analogous thing for singular solutions, solutions that the leading term is behaving like 1 over R to the L plus 1. And you can get a dual family, some singular solutions. This singular solution, and I'm going to just spend a few seconds on this slide. So there is regular solution and there are singular solutions. And it is a fact that there is some rational isomorphism between them. From some general theory, when you have such a rational isomorphism, you get canonical filtration on each fiber of the where you start with and where you end up with. And with this information, I can treat the last slide. So I have defined, and we spend a lot of time on regular solutions. I briefly said what are singular solutions, but you can think of them as solutions that behave as singular near the origin. There is some twist, some dual of singular solutions that is done using this anti-holomorphic involution. And it is a fact that there is an intertwining operator. There is a map, a rational map between the singular solution and regular solutions. Regular is this dual to singular solution, and it is unique up to multiplication by regular by rational function. All of this is in this abstract algebraic setting. But the next thing that I'm going to say is how we can recover physical solution out of these abstract algebraic families. So first statement is how you can get the spectrum, the collection of real numbers that physicists obtain. So the claim is that you can get the spectrum in the following way. It's the collection of all complex numbers such that the fiber regsol over this E, I told you that such an arrow gives rise to filtrations, such that the fiber here in this side, it has a non-zero infinitesimally unitary Janssen quotient. If you have a filtration, it has a corresponding quotient. This quotient is called infinitesimally unitary if it carries some invariant Hermitian form of definite sign, which comes from free in some cases out of this map. So using this Janssen quotient, you can get the spectrum. Second statement is that you want to recover solution space, physical solution. So if you take such a number in the spectrum, a real energy, then it has a unique infinitesimally unitary Janssen quotient. And this quotient is canonically isomorphic to those solutions that the physicists obtained as a classical GK module. The last statement is about bounded spectrum, but I stole 3 minutes out of your time, so this is enough. I'm sorry for the delay, and thank you very much for listening.
Thank you very much for that. And this is the time for your questions.
Can you please explain the discrete spectrum? The variant?
Can you get closer to the computer, or maybe G can repeat the question? It's hard for me to hear.
You can describe the discrete part of the spectrum.
To describe the discrete part of the spectrum. Yes, so this is what I skipped. So the discrete part of the spectrum, you can describe it in the following way. We have fibers of this map, and they carry filtration. Filtration, in one side it's an increasing, in the other it's decreasing. A filtration can be simple, trivial. Trivial meaning it has two pieces. One is zero, the other is everything. And it can be non-trivial if there are interesting pieces. Think about composition factors, some parts which are interesting and are stable under all those actions. So the bounded spectrum, it coincides with all those points in the base, all complex numbers, for which this fiber above E, it has a non-trivial Janssen filtration. Namely, the filtration has more than just two pieces of zero and everything. There are some pieces in between. It also means, because of this statement, that generically for all complex numbers which are not belonging to the bounded, to this discrete part of the spectrum, the abstract, this algebraic GK module is irreducible, infinite dimensional. The issue is that it's not related to physics, not to the extent that I can say anything.
May I ask a question? So,
Sure.
Is it somehow relevant for what you described, the fact that the hydrogen atom is super integrable system?
Yes, yes. The fact that, in a short way to say it is, let me see if I can find this slide fast. So the fact that something is super integrable gives you, in a simple words, you can say it gives you some relations, polynomial relations between generators, some non-trivial relations. These non-trivial relations are related to the way, in this case, to the way in which some central element acts, some element in the center of the enveloping algebra, which you can also think of it or approximate this to, you can relate it to the Casimir you can relate it to the Casimir of this family G. So the superintegrability can be related to the way the Casimir or the center of the universal enveloping algebra G acts on solutions.
I have a question. So you defined these algebraic families of, let's say, for example, of Lie algebras, and you gave some examples. And for example, in the complex case, we have let's say, two Lie algebras which are involved. I mean, for example, we have SO4, and then we have the Lie algebra of the Cartan motion group. Do you have any example where we have two complex Lie algebras which are semi-simple? I mean, both are semi-simple.
So what? So yeah. So typically, what we can describe is we can relate if you have a complex algebraic group, not necessarily reductive, and if you have two real forms of it. Real forms comes from anti-holomorphic involutions. There is some technical condition which is generically satisfied for almost all real forms. You want the anti-holomorphic involutions to commute. You can build a family of complex algebraic groups together with the real structure, such that the corresponding family of real groups will connect the two real groups, and there will be some special fiber or special fibers with some semi-direct product. As for two things, as what you're asking, no, I don't. Maybe there are some trivial things like that I can explain to you later on. But in general, no, we do not. We do not. The families that I consider, that I work with, if you throw away the special point, they are essentially constant. All fibers away from finitely many points are isomorphic as complex groups. But you can do some things. You can treat your groups, the groups that you define, you can treat them as real Lie groups, and see if they, for example, they are real forms of some other complex algebraic groups. We can talk about it more later on if you'd like.
Maybe I have one more question. As you told us at the very beginning, the procedure somehow rely on whether we take a parameter t bigger or less than 0. And if I'm not wrong, this parameter has the physical interpretation. It's an energy. Do you have in mind another kind of parameter with a physical interpretation, which would lead us to this net of groups?
So that's some.
Yeah, according to the value of this parameter.
So I don't have an example such nice as this one. It was mentioned. This is a super integrable system. Things here are very nice in some sense, but in the past I was working on the motivation for dealing with families came to me by I studied contractions. Contractions are some limits of Lie algebras, Lie groups in physics, which you can also use this language to describe. And you can think of familiar cases where you look on this, what's the name, like correspondence principle. You can think of 1 over the speed of light as a small parameter, or the speed of light as a big parameter, and you can say obtain out of relativistic mechanics, Newtonian mechanics. You can take the Poincaré group and get in the limit the Galilei group. You can think about H Planck as a small constant. You can do similar things for Lie algebras, but not as nice and clean as what I'm showing you here with this extra differential equation and solution. It is not that impressive, but yes, you can do. Yes.
Maybe I have a question. So from starting from the beginning, you were taking this difference between explicit and implicit, I don't know, remember if this was the adjective that we were using, symmetries of a physical system. I think we have these implicit symmetries that are really not symmetries of the Schrödinger equation, but rather symmetries of some spaces of solution. Do you have any concrete example in which we cannot solve the Schrödinger equation, but we know that there is a space solution with a certain given symmetry?
No.
We cannot.
No. I mean, if it was a talk in a physics department, I would start and say, I'm not going to give you any new physics. It's the same solutions, it's the same answer at the end for the physical problem. What I'm pointing at is I'm pointing on some extra structure, which you don't have to use to solve, but in my opinion, it's nice to know. It suggests something which is, I don't know, on a philosophical level, very interesting. It suggests that the system of the hydrogen atom it's algebraic in this parameter energy, the complex parameter energy. It's algebraic, it is more than analytic. It is polynomial in the energy. If you split things according to those quantum numbers, you get scalar functions depending on the energy, on those separation constant, and these functions are polynomial functions. And it means that you need to know them. If you know them on a Zariski dense subset, if you know them on a sequence, converging sequence, you know them everywhere. So if you are a physicist, if you want to do an experiment and you don't have any money, you don't need to go to higher and higher energies. It's enough to have more and more samples of a system in a bounded region of energies. I mean, this is some idea that I don't know how to make into some experimental thing, but it's an interesting idea that physical system behave very regular, very well in the energy, and the energy in some sense is defined for any complex number.
Okay, thank you.
Some probably related question on it before. So you can think of hydrogen atom as harmonic oscillator in quantum mechanics. So does it show up somewhere here, or does it help somehow? Because then you solve completely algebraically, right?
I'm sure you can do things with that. There is also some hidden symmetry, different type that you see for harmonic oscillators, some UN symmetry. But I don't know enough to give you some more reasonable comment. I do think that I can comment. This is if you want something which is not complete. So this harmonic oscillator is related to the shale representation, to the metaplectic representation, and there is an analogous representation here of some larger orthogonal group of, if you're familiar with this dynamical symmetry of O42 or SO42. And this is something that I work with. I think that this representation, this minimal representation, plays some role in this description of families, but I cannot tell you more than just feelings right now. Maybe in a year or so.
I'm thinking about another question. It's well known that once you go from classical to quantum physics, you might lost some symmetries. Is it also somehow well seen or expectable in the procedure you gave us?
I don't know. I don't know.
Okay.
I don't
But
know.
it's a kind of expectable that also hidden symmetries might be lost through this procedures. So yeah,
I don't know. I'm sorry.
Okay, so whether there's no other question, would like to thank you again for a nice talk.
Thank you very much.
Thanks for taking part in our seminar.
Yes, I'm happy that there were no technical issues. Thank you very much. Take care. Bye-bye.
Bye-bye.